Hi, my name is Patti. I am a third-year graduate student in astronomy here at UW. I'm an astronomer. Cool, right? I get that a lot. That's usually people's first reaction when I tell them what I do. But I quickly realized that they don't really know what I do at all. First things first, I'm not an astrologer. I can't read your horoscope. You laugh, but it's kind of sad how often that confusion is made. Further, I'm a subset of astronomers. I study the big picture of the universe. I'm a cosmologist, not a cosmetologist. I'm not a rocket scientist. I'm not an astronaut. I'm an astronomer. So let me tell you a little about what I do. Astronomers measure light. Photons are our data. It's not just the light that we see with our eyes, but all different kinds of radiation. From the radio waves, microwaves, infrared radiation, which we feel as heat, UV rays, which give us sunburns, gamma rays, X-rays, all different kinds of radiation. We're developing the telescopes, the cameras, and the tools to detect, and powerful software to analyze. So let's start at the beginning. We believe the universe began with a big bang. It rapidly inflated from smaller than an atom to the size of a galaxy in an instant. What we actually observe of this is the fingerprint of the Big Bang. This is called the cosmic microwave background. It shows us the initial matter distribution of the universe. It's as far back as we can see. It tells us something about the Big Bang, what happened before it, but it also gives us a starting point from which we can evolve simulations of the universe. If our cosmological model, if our theory is right, then we can evolve from this starting point in a computer and have it come and match what we actually observe. What do we actually observe? Let's zoom out from the Milky Way here. These are all galaxies we've observed. This is all data from the Sloan Digital Sky Survey. As we move further and further out, we're also looking further back in time. This is because light takes time to travel. If you have two cars arriving at the same time, and they both are traveling at 60 miles per hour, but one car came from twice the distance, well, that car must have started sooner. It must have started at an earlier time. So the further away we're looking, the longer it's taken that light to get to us, the further back in time we're seeing. You can see the large-scale structure of the universe here. Galaxies cluster along these filaments, and they fall into these superclusters. And there's large voids, bubbles of emptiness. We're zooming out now to the cosmic microwave background, which as far as we can see, it's this bubble that inhabits our universe. You can see that there's a lot of empty space in there between the CMB and what we've observed as far as galaxies go. That empty space is what we call the cosmic dark ages. It's this period of time after the CMB was emitted that it took hundreds of millions of years for the first stars and galaxies to form under gravity. Gravity pulls the matter together and it ignites, and the first light starts being emitted. There's not nothing during the cosmic dark ages. There's just very little light coming to us, and light is our data. So it's hard to know much about it. But it's a fundamental piece of the cosmological puzzle. If that puzzle were a pie chart, it would look something like this. 4% of the universe are made up of star stuff, as Carl Sagan would say. What you and I are made of, planets, galaxies, stars, dust, gas. 96% of the universe is dark matter and dark energy. Dark is a sort of blanket term we use to describe these things which don't emit light, and so it's hard for us to know much about them. But we don't know nothing. Dark matter, for example, has a lot of gravity, and that gravity bends light like a lens. So this cluster of galaxies you see here in the center has a lot of dark matter, and it bends the light from background galaxies around, creating these arcs of magnified mirrored images of background galaxies. And by the amount of lensing that's happening, we can measure how much dark matter is there. Now, dark energy is a separate entity. It was predicted by Einstein. It was a constant in his equation, but we hadn't yet measured that the universe is expanding. So he didn't really believe it. He discarded it as a fudge factor. We then measured the universe as not only expanding, but it's expanding at a faster and faster rate over time. Faster and faster, it's accelerating. Dark energy is that something that's causing this acceleration. It opposes gravity, and we don't really understand it. Discarding that constant was Einstein's self-proclaimed biggest blunder. It's now a standard, integral part of the standard cosmological model. We now have the tools to begin to peer into the darkness. This is the Murchison Wide Field Array. It's a first-generation telescope of its kind. It probably doesn't look like any telescope you've ever seen before. It's designed to start to look into the cosmic dark ages by measuring light that's emitted from neutral hydrogen gas, very weak emission, in the radio part of the spectrum. The MWA is close to my heart. This is what I do my research on a daily basis. This is my research group. This is only a handful of the people that were affected when the NSF decided to discontinue funding for the MWA. This is where my research intersects with policy. In 2010, the National Academies conducted a survey and published a list of priorities for astronomy research for the next decade. The MWA was mentioned by name as addressing, its goals were addressing the top priorities listed here. And this book was written in part as a guide to science policy, as a guide to politicians, to the public, to make informed decisions. So the only reason the NSF would deny funding to a top priority project in astronomy is if there's just not enough money to go around for basic research. And that's true. There's not. Funding is being cut. Obama wants to increase funding, and he's working on it, but it's just not enough. I believe it's because people and politicians especially don't understand what basic research is and why it's so important. Basic research, this quote, is from a report by the NSF when it was first created 70 years ago. Basic research, directed simply toward more complete understanding of nature and its laws, embarks upon the unknown, enlarging the realm of the possible, with applied research then being to convert the possible into the actual. It's hard to grasp, though, what basic research is. It's the process of discovery motivated purely by curiosity. It is unadulterated search for the truth. But it's kind of a black box as far as politicians and taxpayers are concerned. They're throwing their money and they're not sure what's going to come out of it. It takes experience and history, really, to show that this black box is always fruitful. The more we know, the more we discover, the more we can harness that knowledge and apply it. That's why basic research is so important. As I mentioned before, radiation is our data. We must develop these tools to detect the radiation, very, very sensitive, powerful tools that wouldn't be developed otherwise. And those tools find their way into our everyday lives. The MWA, for example, promises innovative contributions to heliospheric and ionospheric sciences, solar science, and space weather. Space weather, it's critical for GPS, satellite communications, power grids, even airline flight paths. The James Webb Space Telescope, how many people have heard of the James Webb Space Telescope? A handful. A lot of people haven't. It's the next generation Hubble Space Telescope. Hubble's only going to last a few more years. They're not going to keep servicing it. The last servicing mission was in 2009. JWST was nearly terminated by Congress last year. That would put the field of astronomy at a standstill for decades. It's still on the ground. It's not going to be flying until probably 2018, but technologies developed for the JWST have already found their way into the common sector. Optical sensing technologies are being used by eye doctors to more efficiently measure the eyes. Infrared detectors now are not only the standard in astronomy and aerospace, but are used for national security missions and earth science. Large-scale computing is another technological driver. Theorists need fast, powerful computers to model the universe. And lastly, cosmology is central to our sense of what it means to be human. Whether you realize it or not, it affects your ethical decisions, your religious beliefs. Calvin and Hobbes puts it very nicely. The medieval Dark Ages, after the fall of the Roman Empire, were characterized by intellectual stagnation. We need to fight policy that increasingly limits basic research funding, because that will bring about intellectual stagnation. We need to prevent a modern Dark Age before we can enlighten the cosmic darkness. Thank you.